This video is a summary of the ways you draw in an IGCSE physics exam. It will cover spectrum of questions from motion to waves to light waves, and will also cover how to do some of the graphs. So let's start with the first question. If you don't know any of the lessons, I suggest that you go back to the channel and look through the lessons first. Now the first question says that a bus travels from one stop to the next. The journey has three distinct parts. Stated in order they are: uniform acceleration for 8 seconds, uniform speed for 12 seconds, and then non-uniform deceleration for 5 seconds. Figure 1.1 shows only the deceleration of the bus. On figure 1.1, complete the graph to show the first two parts of the journey. So the last one is shown over here. Now let's look at our scale first. This is 5, 10, so this should be 15, and we have 20. So this is 25. The last part is shown, which is from 20 to 25. There was a decrease in speed. Now before that, it was constant acceleration. So I'm going to draw a line from this point for 8 seconds. But let's able the 8 seconds first. This is 9, this is 8. So from here, it was accelerating, constant acceleration, uniform acceleration, and then at this point it was traveling at constant speed, and then non-uniform deceleration. So let's draw, take a line, different colors, use colors, and then another line from the starting point to that point. And that's how you answer this question. So next we'll go to vector forces. So let's look at this question. It says that figure 3.1 shows the top of a flagpole. The flagpole is held vertical by two ropes. Those are the two ropes. The first of these ropes has a tension of 100 newtons at an angle of 60 degrees to the flagpole. The other rope has a tension T as shown. The resultant force is down the pole. So the resultant force actually of these two is down the pole with a magnitude, and the magnitude is given 200 newtons. In the space below, using a scale of 1 centimeter to 20 newtons, we need to draw a scale diagram to find the value of tension T. So in this example, they gave us the resultant, but they want the value of T. Clearly label the 100 newton, 200 newton, and T in your drawing. Alright, so let's just understand the question. Here we have this force. We have this tension. Of course, the normal way would be to draw the parallelogram. So we extend this. This is also T, parallel to each other. And this thing is also the 100 newton. But of course, so in here they are not drawn to scale. And the resultant of those two is 200 newtons. But this is not up to scale. That's why it's not vertical. So now we are going to do it up to scale and see what's happening. This is 100 newtons, so it should be 5 centimeters based on this scale. This is 200 newtons. So it should be 10 centimeters based on this scale. So let's start with the 200 newtons. Since it's vertical, it's easy to draw. We'll get our ruler, place it in a vertical position. We can compare it in here. So yeah, this looks vertical, but let me get the 10 centimeter mark. Yeah, the 10 centimeter mark is aligned with the dots behind, so this is exactly vertical. We draw the line. I'm going to draw lines with the black color up to 10 centimeters. Yes, exactly. So this is the first one. And then at an angle of 60, we need to draw 100 newtons, so 5 centimeters. From the tools, we get the protractor. We adjust it. This is our starting point. And from this side, we go 60 degrees. So this is 60 degrees. And then we take our ruler. We know we need to draw a line of 5 centimeters. So I'm going to line it at the 5 centimeter mark. So this is the 5 centimeter mark, but make sure it's exactly on. Alright, now we can get rid of the protractor and we draw the line. We label. This was the 100 newtons, this was the 200 newtons, connecting between them, between a line, and that should be our tension T. Of course, we could have drawn the completion of it. We could have drawn the T over here and then the 100 newton, but it's not really necessary. We already have our result. This was our starting point. This is the end point. So we take our ruler, take measurements. Yeah, this is 8.7 centimeters. So 8.7 centimeters, multiply that by 20, and you should get 174 newtons. Alright, now let's go to another example that involves waves. Sound from a loudspeaker is traveling in air towards a solid wall. figure 7.1 shows compressions of the incident sound wave and the direction of travel of the wave. As it strikes the wall, the sound reflects. Complete figure 7.1 to show the positions of 3 compressions of the reflected sound wave. Okay, so this is a reflection example. We have the direction of wave, we have the wavefronts, and we need to show for the wavefronts. Now the easiest is to first draw the direction of wave, continue it until it strikes the wall. So for this I'm going to use the yellow line, extending it till it reaches the wall. Let me adjust from here, it has to follow the same path. Okay, I'll extend it from here just to make sure. Okay, and then at the point where it strikes the wall, we need to draw a normal line. So let me just get the protractor to make sure the angle is 90 degrees. At this point, I'm going to rotate it, and at 90 degrees we draw a normal line. Now the normal line should be a dotted line, so any dotted line I'm going to represent with, let's say, with green. So this would be our dotted lines. So from here we are going to draw a line exactly on the 90 mark. That's our normal, and as you can see the angle of incidence is 10, 20, 30. We count from here. So that's 30 degrees, which means after another 30 degrees from this point, another 30 degrees, let me take this and label, which will become at the 60. That would be the new direction of travel of the wave. That's the reflected wave. Alright, we don't need the protractor anymore. Make sure you label the directions. This is the old direction and this is the new direction. Now we are going to draw the new wavefronts. This is the direction of the wave, but we didn't draw the wavefronts yet. And to do that, we need the protractor again. The new waves, after the wavefronts hit the wall, the new waves must be perpendicular to the new direction of travel. So let's see how would that look like. Place this thing over here, and from this side, we are going to draw from here the first reflected wave. And we do the same from another point from here. So I'm going to draw another one, the same also for the last one. Make sure this is on it. The line over here is exactly with the normal, and then we'll just draw. And yeah, this looks it. Now, so if this was the old direction, this is the new direction. You know, the direction must be perpendicular to the wavefront. Okay, so let's look at another question. Now this time we are going to do diffraction. Those are the waves that are going to diffract after they pass through the barrier. You can compare the size of the gap with the size of the wavelength. So as you can see, the wavelength in this case is 1.5 centimeters, but the gap is also about 1.5. So they are about the same. So this is what we are going to do. We place a dot at the center of the last coming towards the barrier. And then we take the compass. We measure the wavelength, the first wavelength. We make sure the radius is the same as the wavelength. This is slowly, and this is the first wavelength. So we draw the first diffracted wave. You can erase the parts later, or be careful when you draw from the start. Next thing, you'll increase the radius till you get double the wavelength. Then when you select the pen, this is where you select to draw. And then we increase the wavelength, triple, draw again. One more time. 3 are enough, but just do the 4th. Now this is maximum diffraction since the wavelength is about the same size as the gap. You can erase those excess parts, and that's the diffraction. Alright, let's go to the other question. This time we'll deal with light reflection. Now it says over here, a lamp in a large room is suspended below a horizontal mirror that is fixed at to the ceiling. Figure 8.1 shows a scale diagram of the lamp and the mirror. So this is what you see. We need to draw 2 rays from the center of the lamp that strikes the mirror, and then we use those rays to locate the image. This is the center of the lamp, and we are going to draw 2 light rays, and those light rays could be in any direction. It doesn't really matter, this ray or the same point, another ray from here, or another ray. So as long as they strike the surface of the mirror, doesn't really matter. Here I've drawn 3. I'll select just 2 of them. Now from here, first thing, definitely you need a normal compass. Make sure it's, so 90 degrees. Now any normal line, I'm going to select this color. Make sure you draw it as dotted. And yeah, that's about perpendicular. This was the incident ray, and we know it's going to reflect with the same angle. So whatever this angle was, 10, 15, 16, 17, then it should reflect 10, 15, 16, 17. And we'll draw the reflected ray. Alright, so this was the first one. Label the direction. Same goes for the other ray. So the angle of incidence in this case is 10, 20, 30, 31, 32. So it's between 31 and 32. So I'm going to do the same. This is counting. I'm going to count 10, 20, 30, 1. And this is between 31 and 32. So I'm going to select a line, draw it to that point. Make sure you label the directions. Okay, we didn't draw the normal. Yeah, do that. So 2 incident rays, 2 reflected rays. When we extend the reflected rays, now for the extensions it should also be dotted, but I don't have dotted in the options, I'll just use the green color. So from here we extend the ray, make sure it's an extension of it, another extension, let me just check, and yeah, this is the extension, place it then over here. Same goes for this ray, let me just place it here to check the extensions, this is about it. This is the point of intersection, and this is the reflection of the starting point. So then that's where the image of the lamp is. Now in the next question, I'm going to also show you reflection, but without using angles. An easy way to solving it without using the protractor at all. So how to do that? First thing, you find the image, and you can find the image by knowing the distance. You take the ruler. Now from here to the first surface of the mirror, this is 3.9. 3.9 times 2, that becomes 7.8. So at the 7.8 mark, I'm going to place a dot. This is our image. Label it as I. And then from this point, we do the reverse. We start by drawing the extension line. And then from the extension line, we draw the reflected. So this is the reflected ray. Make sure it's exactly on this ray. And this is our first reflection. From the same point, exactly from the same point to here, drawing the extension line. And then from the extension line, we draw the reflected, and that's it. Make sure you label the directions. This is the old direction, this is the new direction. Now we can then draw the normal. It's like we are doing everything in reverse, and we do the same for here. We can also label the angles. So this is the incident angle. For one of them, you label one of them as X. Okay, so this is X, the incident angle. And that's how you do the reflection question. Now the next question, we deal with light refraction. Figure 7.1 shows a ray of monochromatic red light in air incident on a glass block at an angle of incidence 50. So as you can see, without measuring the angles, use a ruler to draw the approximate path of the ray. Alright, so from this point, we know it's not going to move straight. It's not going to bend away from the normal. It will bend towards the normal, up to this point. It doesn't matter, you don't have to know the angle. We know it's close to the normal, but not exactly on the normal, just a bit away from it. As long as it's in between the old path, this is the old path, and the normal. So somewhere in here should be fine. This was actually for red, so it would have been better if we chose red color. Now, of course, the thing about it is that it's going to be parallel after it emerges from the glass block to this incident ray. So I'm going to draw it on top of it, then I'll just move it. Why should those rays be parallel? Well, because this is a rectangular prism. Those sides, this side is parallel to this side. So therefore, if the incident angle is 50, the emerging angle should also be 50 degrees. We don't know the angles in between because we didn't calculate, but definitely the emerging angle should be 50. And don't forget, of course, to label the direction of travel. And then the other part, use a ruler to draw the approximate path of violet ray in the glass block. So definitely violet is going to refract more. Let me choose the violet color. So definitely it will refract more in here, but when it exits, it entered with an angle of 50, same as red, so it should exit with also an angle of 50, same thing. They are not spreading further. After they leave the glass block, they are parallel to each other. If it was a triangular prism, then they would have spread further and dispersion would occur. And this time, we are using triangular prism. So this is our red ray. And we know when it exits, it's not going to go straight. It will refract even further. So this is let's say the refraction of red. Draw the direction. And we also need to draw for violet. So same thing. Violet, when it enters, it refracts more than red. And even after it exits, it refracts even more. That's why they disperse. And why does it refract more? Well, due to the geometry of the shape. Don't forget to label the directions. Alright, next thing. Now this time we need to do refraction and find the position of the image formed by refraction. So let's start by drawing the refracted rays. We can start by drawing the normal, first normal and another one. And then the refracted, we have options either to go straight towards the normal or away from the normal. Now the option is of course away from the normal because it's going from water to air, from high density medium to low density medium. So this is the new direction, and same thing goes over here. They shouldn't be parallel to each other because it's not the same angle. They didn't enter at the same angle. So make sure you don't draw them parallel to each other. If it was the entering angle, the incidence angle for both was the same, then the refracted angle would be the same. But they must diverge a bit. Since this one has more incidence angle, then it should experience more refraction. And then we need to extend them. So we'll extend this ray. Just make sure it's exactly on it. Extension. And next we'll extend the other ray. Just make sure it's on it. So this is the extended ray. And you can see they are meeting at point. This is the point they intersect with. So this should be the image. They label it as J. And that's it. Now in those two examples, we didn't do any calculation, just approximate drawing. So in this example, we have to do it. And from here, we want to first find the angle of incidence. We know definitely the angle of incidence is from the normal line. So therefore, the angle of incidence is 90 minus 35, which would be 55 degrees. So this is the angle of incidence. That's the normal line. And they said the glass has a refractive index of 1.5. We need to find the angle of refraction. Now this case, it's going from air to glass. So we know n equals sine I divided by sine R. N is 1.5. Sine I, which is sine 55, over sine R. It should be sine R equals sine 55 divided by 1.5. And R would equal sine inverse this whole thing. I'm just taking this sine over there because I just want the angle of refraction. So it should be sine inverse sine 55 over 1.5. When you calculate, you do this all at once. Let me show you how. So this is shift sine, and then we have sine 55 divided by 1.5, and your answer is 33. The angle should be 33. So that's what we are going to do. R is 33. Now we take our protractor, and this angle should be 33. Exactly 33, and then we draw the ray up to this point. Alright, now when it exits, of course, we should draw another normal line 90 degrees to the surface, and from there, since it entered with an angle of 55, since the glass is a parallel-sided glass prism, then definitely it should also exit with an angle of 55. Definitely don't forget to draw the directions. Now next thing, Figure 7.1 shows a ray of light traveling in air, incident on a glass prism. So this is an example that would involve total internal reflection. The refractive index is 1.5. It's given, draw the continuation of the light ray until it emerges away from the prism. So at this point, at this entrance point, we know it came perpendicular to the surface, or exactly on the normal line, which means the angle of incidence is 0. Therefore, it's going to continue straight. From this point, it will definitely continue straight. And at this point, we need to draw the normal line. Let's just make sure it's straight. Yeah. So from here, the normal line should be 90 degrees to the surface. So this is the path of the normal line. I'm going to. Now, since this is 60, then this is 30. Since this whole thing is 90, then definitely this angle is 60. So the angle of incidence is 60. We don't know whether this angle is going to reflect, totally internally reflect, or it's going to refract. And how can we find out? By comparing it with the critical angle of the medium. So let's first find the critical angle. By the way, don't forget to draw the direction. So let's figure out the critical angle. Since the refractive index is 1.5, we know that sine C equals 1 over n, which is in this case 1.5. So C should equal sine inverse 1 over 1.5. When you calculate, especially with sine inverse, you calculate all at once. Do not split your calculation into multiple steps. Just do it all at once so that you don't have to deal with the rounding problems. As we said, this is the last thing. Shift sine 1 over 1.5. There, close. The answer 41.8, so about 42. The critical angle is about 42 degrees. Now since it's 42 degrees, the angle of incidence is 60. So the angle of incidence is more than the critical, because 60 is more than 42. This answer C was 42. Therefore, total internal reflection would happen. So definitely we come from here and we have an angle of 60. So 10, 20, 30, 40, 50, 60. This should be the path of the reflected ray, and that's what we are going to do. That's the new direction. This angle was also 60 degrees. So now at this point, still we don't know, maybe it would internally reflect or it would continue to refract. We don't know yet, but we can know. Draw the normal line, and first of all we need to find this angle. So I'll extend the normal just to show you how we can find it. So since this is 30, definitely this should be 60 degrees, and since this is 60, definitely this is 120 because it's a straight line, and this is also 30 because the whole thing should be 90. This is already 60, so this is 30. So what's left? This is a triangle. 30 plus 120, 150. So we also have here another 30. Now this is the angle of incidence, which is this time the angle of incidence is less than the critical. 30 is less than 42, so refraction would occur. And how much refraction? Well, we need to find out. This is now going from glass to air, so we're going to use 1 over n equals sine I over sine r. So 1 over 1.5 equals sine the I, which is 30, and divided by sine r, the angle that we want to find. So from here we can know, making this as the subject, cross multiplication, sine r equals 1.5 equals 1.5 times sine 30, and r would equal sine inverse 1.5 times sine 30. So let's go and calculate. Sine inverse 1.5 times sine 30, and your answer is 48.59, so we can say 49. Take this and make sure the angle is 49, so 10, 20, 30, 40, and 49 should be up to this point, yeah. And then we draw refracted ray. Alright, so that's it. Next, we have total internal reflection in an optic fiber, and this is just, you have to do it for several times. So here you draw the normal line. You can do it roughly, quickly in this one, because as long as you know the whole idea of it. Take your compass, the protractor. So this is over here, you can see the number 166, so we go to the other side, same thing, 106. This should be the path of the reflected ray, and that's what we are going to do. I'm going to use blue until it reaches the other surface, exactly on the line until it reaches the other surface. And then from there we also draw another normal line, and from there same thing. So this is at about 168, so we come over here. Alright, draw it until it touches the surface again, and from this point draw the normal line. It would have been better if you used the protractor to check if this angle is 90. So finally this is about 163, we do the same and we draw the line. Total internal reflection until it exits. And don't forget to label the directions. Alright, so next on our list. So how to deal with lenses. Now it says a vertical object that is 1 centimeter all is to be positioned to the right of the lens with one end on the principal axis. One end of it should be on the principal axis. Draw the object in a position that will produce a real enlarged image. So this case should be between f1 and 2f1. So if this is f1, 2f1 should be somewhere around here. If you don't know what's this case, surf the channel, you will find a video that explains lenses and all the other topics actually. Label this object Q, and then we place an object that is 1 centimeter tall, so we need our ruler. Flip it vertically. So from here we draw, I'm going to use blue. This is the object 1 centimeter tall. Okay, but make sure it's vertical. Now this is an arrow, so let's make it an arrow. One side on the principal axis. Draw 2 rays showing how the real image is formed. Alright, so draw any 2 of the standard rays. Now the first standard ray is that if it goes parallel to the principal axis, which is about here, and then after that it should pass through the focal point. So it should pass through the focal point on the other side, and that's one of the first standard rays. And the other one says that if it passes through the center, then it should continue through the center So this is our second standard ray. You see they intersect at this point. Let me label the point of intersection. And that's where your image is. This is the image of this object. Of course, it's pointing down. It's in reverse. Now this is enlarged. You can see it's larger in size. We should label it with the letter I. So this is I, the image. This was the object O. And we can actually calculate the magnification. So this was 1 centimeter. When we go over here, this is about 1.9 centimeters. So the magnification in this case is 1.9. 1.9 divided by 1, you get 1.9. That's the ratio of magnification. So this is it. Let's look at another question. An object is placed in front of a converging lens. A real image is formed as shown. The converging lens is not shown. So they gave us the object and they gave us the image. Now definitely we know if we connected the standard rays, so if we had one from the top directly to the top of the image, then definitely it should pass. This point on the principal is the center point. Let me label it. This is the center point of the lens. So this is the standard ray. When it passes through the center, then it should continue straight. Now, so from the center point, that's the first thing, we draw the center line of the lens. You don't have to draw the lens, you just need to draw the center line of the lens. And then from there, we can draw another ray, one of the standard rays. So if this ray is parallel to this, then after, from the image, it should pass through the focal point. So definitely this point over here this point should be the focal point. And make sure you label the direction of light rays. And this one is focal point F. And then they want a third possible ray from A to B. So another one would be the opposite. So the third standard ray from here and then should be from this point to this point. Then definitely this point must be F on the other side of the lens. And that's it. Another question about the rays. Here they said an object that is 2 cm high is placed 2 cm to the left of the lens. So we need our ruler. 2 cm to the left of the lens. So let's label this point. Then 2 cm high, exactly vertical. And we draw a line 2 cm high. So this is our object. I'm going to represent it as an arrow. And then the focal length is 3 centimeters. So let me label it. So after 3 centimeters, this should be the focal point. Now the object is between the focal point and the center of the lens. Therefore, you should get a virtual image. Now let's do two of the standard rays. One ray goes from here and then the other one passing through. Now we need to extend those rays. Let me draw the direction of the rays. So let's extend those rays. To extend them, I'll use another color. Same goes from here. Okay, this was short. Let me elongate this. I'm going to erase this one. And that's intersection point. So we're going to label it. And from there, this is the image. Now definitely this is a virtual image, so for the eye, in order for the eye to view this image, well, the eye must be in this position. You don't need a screen. It's unlike the previous cases where you needed a screen because they were real images. Alright, and then you need to find the distance of the image to the lens, so measure this distance and the height of the image. So you can see the distance is 10.5, the height is about 9.5, 9.7. Alright, so that's it. Last thing is just to practice how to do the graphs. So here you have the background count rate in a lab is 30 counts per minute. A radioactive sample has a half-life of 50 minutes. The sample is placed at a fixed distance from a detector. So let me draw the scenario. We have a sample, radioactive, emits radiation, and then you have a detector. And the sample is just radiating in all directions. Radiation hits the detector records. Now remember, the detector records the radiation coming from the source itself and the background radiation. Let me represent background radiation with this color. There's also some background radiation. The source emits a lot of radiation, but on the background there is some of it going towards the detector also. and they already gave you the background is 30, the sample is 310. They want us to draw the graph of count rate from the sample corrected for background radiation. So how can we do that? Alright, so the first thing was 310, so 310 minus the 30, and then you get 280. So from 280, this is 290, this is 280 over here. This is our starting point. Let me label the points. Okay, make sure you are able to read the scale. And then after 50 minutes, so let's use lines. After 50 minutes, which is exactly the half here, 42, 50 minutes. Okay, so after 50 minutes, it should be half of that. So what is half of 280? 280 divided by 2, you get 140. So let's label where is the 140? 10, 20, 30, 40. So this is the point. From here, let me extend it, and that's our point. Okay, you can, instead of the lines, so that we are not bothered with raising them later, we can just use the ruler, place it in a vertical position. That's the 50. Now 140, as we said, this is 10, 20, 30, 40, and this point. So from here it was 140. Goes again, it becomes 70. So where is 70? This is 100, so this is 90, 80, 70. After a time of, when it becomes 100. So this is it. We follow this path until it's 100. And then after another 50, which is 150, again, it's half of 70. Everything we divided by 2, we get 35. So we start from here, this is 10, 20, 35, about somewhere in here. And then we simply connect, trying to smoothly connect the points. You can adjust in here and then erase, try to make it as smooth as possible. That's it. Thank you so much. That was the last question. I hope this was beneficial for you. Don't forget to like, subscribe, and share.